A reaction coordinate diagram is a way to look at the energy landscape of a particular reaction. So let's take a simple elementary reaction in which we're going to call P a protein and L a ligand. And then that's going to form a protein ligand complex called PL. Okay. The important thing is that this is a one-step reaction, okay, it's an equilibrium, and the substrates, or excuse me, the reactants are P and L, and the product is PL, okay? So we can depict that. We can think of looking at a reaction coordinate diagram to look at the relative energy of those two states, including any energetic barriers in between them, okay? So when we draw a reaction coordinate diagram, we don't usually draw axes, but there are implied axes where the y-axis is the free energy. Okay, so as a line goes from lower on the y-axis to higher on the y-axis, the free energy increases, and then again, as the line goes to lower on the y-axis, then the energy is decreasing. Okay. And then the x-axis is the reaction progression. Okay, so going from the beginning of the reaction, where P and L are unassociated with each other, to the end of the reaction where P and L are now associated with each other. Okay, and so what's important about this is to figure out what the relative energies for different features are. So importantly, let's define some terms here. Okay, so we have potential wells. Okay, so these look like, as the name suggests, like wells, like water wells. Okay, so they're kind of energy minima within the diagram. Okay, so local energy minima. And you can kind of imagine if you had a marble, for instance, that fell down the hill, right? This is in one of these two wells is where the, in this case, with there being only two wells in here, the marble would end up in one of these two local energy minima. Okay, and these are called potential wells. All right. Now the maxima, the local energy maxima, all right, are the transition. This is where we find the transition state. Okay. Now, if we project lines, right, at the bottom of the two potential wells. Okay, so the first one being the one that is for the P plus L state, the unassociated P plus L state, and then the associated PL state. Okay, we project the lines and then we draw the line between these two states like this. Okay, this red dashed line here. Okay, that gives us delta G. Okay, so that is the same delta G that we've been talking about since the beginning of the semester. Okay, so the change in Gibbs free energy from the between the reactants and the products. Okay, and in this case, what we see is that the energy goes down. All right, and so one thing we can see by just looking at this is that the delta G goes down, so it's negative. Okay, so that suggests that thermodynamically the process is spontaneous or product favored. Okay, the other feature we're interested in is the difference between the difference in energy between the potential energy. In this case, we have a line drawn from the bottom of the potential well for the reactants and the top of the peak, which is the transition state. Okay, this is called the activation energy, or EA. Now, what's important about this is that these relate to very important thermodynamic kinetic constants that we're going to be talking about over the next few chapters. Right? So, as we've already talked about, delta G is related to the equilibrium constant. Okay, and what this gives us is information about the thermodynamic driving force for the reaction. So again, in this case, we can see that delta G is negative. All right, and so we expect this reaction to be product favored, and that the equilibrium is going to lie somewhere towards the products. To the right of the equation. Okay, what we haven't discussed so much is kinetics, and for now, let's suffice it to say that the activation energy is related to gives us information about kinetics, or how fast the reaction goes from the reactants to the products, okay, which is what we mean when we talk about kinetics. And so the parameters that we're going to be interested in when we're looking at this, and we'll talk about this soon, are rate constants, okay? And so the rate constants are related to this activation energy, and we'll talk more over the next several modules about how the rate constant is related to the activation energy. But for now, just remember that that's what the activation energy is related to.